My name is Andrew Jackson. I'm a geologist with Global Resource Investments, and I'm responsible for technical evaluations of the mineral companies and their properties that Global invests in. I've put together this Ore Deposits 101 series of talks to help non-technical people understand ore deposits, how they form, how they are explored for, how they are evaluated and mined, and how the metals and minerals are extracted from the ore. The talks highlight some of the features of the main ore deposit types that investors in the resource sector may come across, and it provides an introduction to the jargon you'll find in press releases put out by exploration and mining companies. This is the third talk in the Ore Deposits 101 series, and it focuses on porphyries and iron oxide copper-gold deposits, or IOCGs as they are known. These are some of the giants of the ore deposit world. Now, in the first Ore Deposits 101 talk, I discussed how, because of our current mining technology, all the metals that we use are mined from the top 4 kilometers of the Earth's crust. I also showed why the crustal abundance, or the average crustal abundance of metals, wasn't good enough for economic mining, and that nature needed to provide a major concentration of the metals in order to make grades which can be economically mined. You will also remember that nature concentrates the metals by a process of partially melting the crustal rocks at depth and letting them rise through the crust and cool, and then dumping the valueless minerals such as feldspars and quartz, and concentrating the metals in the remaining magma and hydrothermal fluids. In the second talk in this series, I spoke about the deposits associated with mafic layered complexes and kimberlites. In this talk, I'll focus on the porphyry and IOCG deposits, which develop at a slightly shallower depth than the mafic layered complexes, generally in the range of 4 or say 5 to 1 kilometers depth. Porphyry deposits and IOCGs are the world's primary source of copper, and they account for more than 60% of the copper production globally. But in addition to copper, they also supply 100% of the world's molybdenum production, 10 to 15% of global uranium production, and a significant proportion of the world's gold production. In short, they make up a critical group of deposits. So let's start off now with porphyries. Whereas the mafic layered complexes we discussed in the last talk usually developed relatively deep in the Earth's crust, porphyries form at a much shallower depth. Not quite as shallow as epithermal deposits, but not much deeper than them either. Porphyries generally form in and around the magma chambers that feed volcanoes. This is Mount St. Helens a few years after it blew its top. Now, seismic surveys show that the main magma chamber extends from 7 kilometers below the surface down to about 12 kilometers below surface. But the data from the earthquake epicenters shows that there is a smaller magma chamber at a depth of about 2 kilometers, and that is the focus of the seismic activity. It is likely that this upper chamber is where the hydrothermal fluids are collecting and mineralizing the surrounding rocks. Mount St. Helens is a porphyry deposit in the making. The steam you can see rising above the new forming dome in the picture on the left there is leakage of the mineralizing fluids. When it comes to porphyry deposits, there are a number of variations on a theme, and the deposits can be copper only, they can be copper gold, copper molybdenum, or molybdenum only. But regardless of the metal mix, the process of porphyry deposit formation is the same. And let's go through that process. Generally, the parent magma is a product of partial melting of a slab of oceanic crust and sediments, and it is subducted beneath a continental margin. The melt rises up through the overriding continental plate and collects in one or more magma chambers, and eventually erupts at surface, releasing the pressure and building a volcanic cone. Once the eruption is over, the magma in the neck of the volcano solidifies and plugs the vent. The magma then continues to accumulate in the chamber below, and it starts to cool. As the magma chamber cools, from the contacts inwards, barren feldspars and quartz crystallize out, and the remaining melt becomes enriched in melts, volatiles, mainly water, carbon dioxide, and hydrogen sulfide. The volatiles migrate to the top of the chamber and accumulate like the foam in a glass of beer analogy that I used in the first Ore Deposits 101 talk. Now, feldspar crystals take up more space than feldspar melt, and this, combined with the accumulating steam and gas, builds up pressure inside the chamber until the surrounding rocks can no longer contain it. The cool, solid rind to the magma chamber and the country rock above it rupture, and the volatiles escape, carrying their metals into the fractured rock. The fluids have a high salt or sodium chloride content, and the metals are generally transported as chloride complexes. As the metal-rich steam makes its way upwards through the cooler rocks, it condenses into brine, and then the metals start to deposit as the temperature drops below about 350 degrees centigrade. The metals drop out progressively, starting with copper and molybdenum, and then lead and zinc once the temperature drops to below 250 degrees centigrade. If gold is present, it will drop out across the temperature spectrum. Because mineralization relies on this crackling of the carapace around cooling magma chamber, the mineralization is associated with a dense network of fine veinlets rather than a few major veins. Mineralized veins are often only a millimeter or two across, but the grade comes from the high density of veinlets. The host rock is progressively altered by the hydrothermal fluids that pass through it. Initially, the iron and magnesium-bearing minerals, such as biotite, amphibole, and pyroxene, are altered to chlorite, actinolite, epidote, and calcite, giving the rock a greenish tinge. This is the proprolitic alteration that you hear geologists talking about, and you can see an example of it in the photo on the left of the screen. On the margins of the magma chamber, where large volumes of groundwater pass through the rock, driven by convection and the heat of the intrusion, feldspars break down to cerussite mica, giving the rock a creamy color, as in the photo on the top right. This is termed phyllic alteration. As the alteration progresses further still, more silica and potassium is added to the rock. The chlorite, amphibole, and pyroxene that were formed earlier are altered to biotite, magnetite, and the plagioclase and orthoclase feldspars are altered to potassium feldspar. This is referred to as potassic alteration, and is the best host for the mineralization. In other words, the more altered the rock, the more progressively altered, the better the chance of mineralization. The rock on the bottom right has suffered this potassic alteration. Pink-orange mineral is potassium feldspar. The sulfide minerals can't be seen in this photo, but they're generally hosted in those grey siliceous veinlets. These alteration types become important in the exploration for porphyry-style mineralization, as they provide vectors to the mineralization. This primary mineralizing event yields only low-grade mineralization. Grades of 0.3 to 0.9% copper, less than 1% or almost always, are typical for primary grade porphyry mineralization. with each pulse of fluid it's tending to enrich the final grade. More pulses of fluid, the higher the final grade. The mineralization frequently forms a halo around the intrusion, both in the intrusion itself and in the surrounding host rocks. It's marked in the red hatched pattern in the cross-section. Now, although primary porphyry mineralization generally has pretty modest grades, subsequent weathering and erosion of the porphyry may produce high-grade secondary deposits of copper, just below the water table. The oxygen above the water table allows primary copper sulfides, such as chalcopyrite, to break down to soluble copper salts. These percolate down to the water table with the rainwater. Once they reach the water table, oxygen is cut off and the water becomes reduced, causing copper sulfide in the form of chalcocite to be deposited. Chalcocite has a higher copper content than chalcopyrite, and grades of 5 to 10% copper in laterally continuous horizontal beds are not uncommon. This secondary enrichment may kickstart the production of an otherwise mediocre porphyry deposit. Following erosion, many porphyries are covered by sediments or younger volcanics. So how do we explore for a deposit like this, which is completely covered by barren, younger rocks? Well, let's back up a bit. We know that porphyries form under large subduction-related volcanoes, and that most of these are located under the ring of fire around the subducting Pacific plate. Another fertile subduction zone occurs in the Balkans, Turkey, Iran, and Pakistan. So this gives us a start in deciding where to focus our exploration. Because of the extensive subduction during the Tertiary, i.e. in the last 65 million years, many porphyry deposits are of this age. In other words, porphyries are relatively young by geological standards. Just to put that comment in context, although 65 million years sounds a long time ago, if the Earth's history were compressed into the equivalent of a single year, the Tertiary would occupy just the last 5 days of December. So once we've focused our exploration on the subduction zones, where porphyries could potentially have developed, we need to find the actual intrusives and their associated mineralization. How do we do that when the mineralization may not actually outcrop? The key to porphyry exploration is the alteration of the surrounding rocks that occurred during the intrusion and mineralization, the so-called propylitic, phyllic, and potassic alterations I spoke about. Identifying the distribution of alteration allows us to vector into the mild, low-temperature propylitic alteration and then towards the hotter, more intense potassic alteration that generally hosts the bulk of the mineralization. In porphyry exploration, if you don't see significant alteration, you're probably not close to mineralization, unless the rock postdates the mineralizing event. Delineation of the alteration can be done in several ways. Obviously, if the alteration outcrops, straightforward field mapping will identify the telltale alteration minerals, chlorite, calcite, and epidote of propylitic alteration, quartz, cerussite, and pyrite of phyllic alteration, and potassium feldspar, biotite, and magnetite, quartz and base metal sulfides of potassic alteration. There's no proper substitute for getting on the ground and mapping an area in detail, but there are other ways of vectoring in on the most prospective areas prior to expending this boot lever. And satellite imagery is one of these tools. The image is a visible spectrum satellite image of a porphyry mine in the Chilean Andes. You can see the open pit and the leach pads, as well as the white dust-covered area surrounding the mining operation. Beyond that, you can see the brown and grey volcanics. What you can't see is the mineralization and the alteration of the volcanics. Reprocessing that exact same image for an invisible infrared portion of the spectrum shows up this alteration as green in the case of argillic, or pink or red in potassic alteration. From this you can see that the open pit is pink and purple in colour, reflecting the potassic alteration of the ore. But there's a strong circular area of pink potassic alteration to the north of the existing pit that probably warrants drilling. There are a couple of other smaller spectral anomalies that should also be checked out. You can see other pink areas down on the bottom left, for example, and some of these may indeed be potassic alteration, but others are probably false anomalies caused by volcanics that are naturally rich in potassium feldspar, rather than caused by hydrothermal alteration. Satellite imagery, as with most forms of geophysics, usually generates a large number of false anomalies, as well as a few real ones. Sorting out the true from the false is largely a matter of experience and then field checking. Satellite imagery works very nicely if the alteration outcrops at surface, but if the porphyry has been partially eroded and then covered by later post-mineralization volcanics or sediments, satellite imagery can't penetrate below the surface, and so it's of limited use. If the alteration isn't within a couple of millimeters of the surface, literally right on surface, the satellite will simply not see it. In this case, we need to use geophysics to penetrate the overlying rocks and see what's hidden below. And there are several geophysical tools that can assist. The quickest way to detect the intrusers is by using airborne magnetic survey. The potassic alteration process generates magnetite, and so it may give a positive magnetic anomaly. The image shows the magnetic data over Kinross's Fruta del Norte area in Ecuador. The epithermal gold mineralization at the top of the image is not detected by the magnetics, except as a break between the blue and the green, which may indicate a fault. However, a blind porphyry intrusion, the camp porphyry on the left of the image, stands out clearly on the magnetics. Unfortunately, at this stage, this porphyry is too low grade and too deep to be economic. A second geophysical method is induced polarization, or IP. This entails putting short bursts of current into the earth through electrodes and then measuring how long it takes for the signal to dissipate. This signal detects disseminated sulfides, but not massive sulfides. The shortcomings of the method is that it's generally reliable only down to 250 or 300 meters depth, although some of the newer systems may extend this to about 500 meters deep. If the cover rocks are thicker than that, or weathering has oxidized the sulfides to deeper than this, IP is of little use. A third method of geophysics that may possibly be able to detect exposed but not buried alteration is radiometrics. It's usually flown at the same time as a magnetic survey and can detect radiation from the potassium in potassic alteration. The lower image is of the Mount Milligan porphyry in British Columbia, and the potassic alteration stands out clearly on the radiometrics as a high purple magenta blob on the top left. Now, all three of these geophysical methods are indirect, used to detect the alteration and not necessarily the mineralization. We still don't know how much copper, gold or molybdenum the rocks contain, and whether they have received enough upgrading from the crustal average to be economically mined. We need chemical assays to determine this. This may entail straightforward surface sampling if the mineralization outcrops near surface. Stream sediments geochemistry is a cheap method of first-pass evaluation. It involves assaying samples taken from stream beds, working on the principle that the sediment has been eroded from somewhere in the catchment area of that stream. Samples are usually taken from so-called second-order streams, the ones that drain only a limited catchment area, so it's possible to narrow down the source of an anomaly pretty quickly. The image shows the results of one of these surveys, again from Kinross's Fruta del Norte concession. The anomalous red samples identify 3 catchment areas that warrant further follow-up fieldwork. Stream sediment anomalies are usually followed up with a regular grid of soil sampling to identify the source of the stream sediment. Anomalies can be very tightly defined using soil geochemistry, and usually well enough to allow you to site a drill hole. As with almost all ore deposit types, porphyry targets need to be drilled eventually to quantitatively determine actual copper, gold and molybdenum values in the identified mineralization. I'll talk more in detail about drilling and drill techniques in a later presentation. As I mentioned at the start of the talk, porphyry deposits are low grade but generally very large. As a result of the low grade and size, few porphyries can support expensive underground mining techniques, and most are mined by open pit methods. This picture is of Bingham Canyon in Utah. An aerial shot like this doesn't give a true idea of just how big the pit is, and you need to get on the ground to appreciate that. This is a photo from the edge of the pit, and you can start to get an idea of the scale from the trucks climbing up the haul roads within the pit. But you only really get a full understanding of scale when you see one of those trucks standing next to a normal SUV. A Cat 797 has wheels 12 feet high and carries a payload of almost 400 tons. The driver probably barely noticed when he drove over this SUV. Everything about porphyry deposits is big. Here are some of the biggest porphyries in the world. You can see that these range in size from 2 billion tons up to Chuquicamata at a whopping 16 billion tons, with a pit that is over 800 meters deep or 2,600 feet. Bingham, which I showed a couple of slides back, is a relative baby in this family. Few economic porphyries are smaller than 100 million tons. But although they're big, they're very low grade. Here are some of those same deposits arranged in order according to copper grade. They range from 0.5% copper up to just under 1% copper. Compare those grades to those at Tenke Fungurume in Congo, with an average copper equivalent of 5% copper, and you can see why they have to be big to make a profit and compete. Tenke Fungurume is not a porphyry deposit. It's one of the Central African copper belt style of deposits. If you take into account the probable cutoff, you can see how small the margins are. Porphyry deposits are very sensitive to metal prices. These examples are some of the Cadillacs of the ore deposit world, but other lower grade porphyry deposits can become uneconomic with just a 20% drop in copper price. Here are some random drill results from Serengeti's Konika property in British Columbia, which is more typical of the recent porphyry discoveries. Intercepts with checks against them are potentially economic. The others are probably not. So you can see that maybe only 50% of those intercepts might possibly make any money. Okay, let's have a quick look now at how porphyry ores are treated and the metals extracted. There are two main process streams, one for sulfide ores and the other for ore that has been weathered to oxidize the sulfides, the so-called oxide ores. All ore in the pit is drilled and blasted and loaded into trucks and hauled for treatment. If the ore is unoxidized sulfidic ore, then it needs to be crushed and milled to a fine slurry. Then it gets passed through flotation cells in a concentrator to separate and concentrate the sulfides. The top picture shows the interior of a large concentrator, with rows of individual flotation cells. The flotation agent is added to the slurry and stirred. The flotation agent preferably sticks to the sulfides minerals rather than the waste minerals, and then air is bubbled through the mixture and the flotation agent traps the fine bubbles which carry the sulfides to the surface of the cell, where they are carried over a weir and separated. From there they are dried to provide a concentrate, which then goes on to a smelter. This is the same process for both copper and molybdenum porphyries. The smelter is basically a large furnace which melts the concentrate and drives off the sulfur to leave molten copper metal. This still contains impurities, and it needs to be refined further to make it a saleable product. Okay, returning to the overall process, that is the process for the sulfide ores, and the oxide ores, as I said, are treated differently. Direct from the pit, the oxide ore is piled onto large lined leach pads and sulfuric acid. The top photo shows one of these leach pads with a new thick black plastic liner visible on the right of the pad. The copper oxide minerals are dissolved by the acid to give a blue copper-rich solution, mainly of copper sulfate. This solution is tapped off from the bottom of the pad and placed into big tanks with steel plates. An electrical current is passed from the tank to the steel, which is then electroplated with the pure copper. This process has the advantage of avoiding the smelting and refining stages required for sulfide ores. Okay, I'm now going to move on to a different but closely related group of deposits, the skarn deposits. Skarns are formed when hot magma intrudes limestone. The fluids from the intrusive alter the limestone to form an exoskarn. The intrusive also assimilates the limestone, altering its composition and forming an endoskarn. Either exo or endoskarns may host mineralization. Skarns are often striking-looking rocks containing red garnets and green pyroxenes. Grades may be high with splashy-looking assays, but they're usually relatively small and irregular in shape and patchy. As a result, they are tricky to evaluate by drilling. In addition, the ore tends to be very hard, and it has a high work index, so milling costs are high. There are some notable exceptions to the tendency to produce relatively small deposits. These are the Erzberg, Kucing and Big Gossen skarns, developed around Freeport's Grasberg porphyry in Indonesia. These skarn deposits are truly world-class, but they are very atypical. These skarns are truly amazing deposits. The picture on the left of the slide is the Grasberg pit, developed on the Grasberg porphyry. There are a number of other smaller intrusions in the area, and several of these have developed the skarns. The picture on the right is of the old abandoned Erzberg pit, the very first one that led to the discovery of the Grasberg complex. That skarn had a high enough grade to allow it to continue to be mined from underground. The Big Gossen's copper-gold skarn deposit is the highest grade deposit in the Grasberg area. Reserves of 37 million tons at 2.7% copper, 1 gram per ton gold, and 16 grams per ton silver. That's about $240, $250 a ton rock. Grasberg and Erzberg are almost an equator, but because they're over 12,000 feet in elevation, they receive snow from time to time, and there's even a nearby permanent glacier. The third and last group of deposits that I'll talk about today are the related iron oxide copper-gold deposits, or IOCGs. I've clumped IOCGs with porphyries as they are also loosely associated with large felsic intrusions and form at moderate depths. Unlike the dominantly tertiary porphyries, IOCGs tend to be much older and are generally Proterozoic in age, from 1.1 to 1.8 billion years ago. There are some younger ones, but they're in the minority. IOCGs tend to form at 4 to 6 kilometers, similar to porphyries, and are invariably associated with crustal scale structures. Crustal scale means that they penetrate well down into the crust, often 20 kilometers deep, and they have strike lengths measured in tens or hundreds of kilometers. The key to the formation of IOCGs is that there has to be an abundance of oxidized groundwater in the country rock to mix with the magmatic water derived from the intrusion. The intrusion of hot water into water-saturated rocks means that the water flashes to steam and this fractures the rocks and produces breccias. The high iron content and oxygenated environment means that the alteration is characterized by abundant red hematite and black magnetite, both oxides of iron. Where do we find IOCGs? Well, they're scattered around the world, but because of their common age, they're usually found in Archean or Proterozoic terrains. IOCGs are highly variable in metal content, and they range from pure iron deposits, such as Carajás in Brazil, to predominantly copper deposits, such as Candelaria in Chile, to copper uranium deposits, such as Olympic Dam in South Australia. In truth, IOCG is a bit of a SAC term, and it covers a multitude of variations on a theme. In size, they vary from the monstrous Carajás at 18 billion tons, 50% bigger than Cuchicamata, which is the biggest porphyry in the world, and down to tiny deposits at just a few million tons. Grades of the copper-rich IOCGs are generally low, similar to those of porphyry deposits, in other words under 1% copper, although some may return long intercepts with over 1.5% copper. Chariot's Marcona project in Peru is 347 million tons, grading 0.71% copper. Carrapateena in South Australia has some unusually high intercepts, such as 178 meters at 1.83 copper, but in spite of its relatively high grades, Carrapateena is struggling to overcome its depth of burial and the resulting cost of mining. This is a cartoon section through the Olympic Dam IOCG system. You can see the deep intrusive in purple, feeding up through the pink granite basement. The deep magmatic fluids from the source intrusive mix with the oxidized fluids from the overlying green basalts and surface sediments to deposit a variety of copper sulfides. Below the water table, chalcopyrite is deposited along with pyrite. At and above the water table, chalcocite and bornite are deposited. Chalcocite and bornite have a higher percentage copper than chalcopyrite, and this zone, at the paleo water table, is the most likely portion of an IOCG deposit to reach economic grades. In South Australia, where both Olympic Dam and Carrapateena are located, grade is particularly important because of the thick sequence of barren rocks that overlie the deeper mineralization. Olympic Dam is covered by 350 meters of barren material. Fortunately, it was high enough grade to allow Western mining to initially exploit it from underground. Only now, 24 years after beginning operations, are they considering developing a super pit. Similarly, Carrapateena is overlain by 450 meters of barren material. Its economic viability is in doubt. IOCG ore is often striking to look at, and it is often very red from the hematite content, blue from bornite, or yellow-green from various uranium oxides. You can see some of the ores from Olympic Dam in this photo. This awesome-looking core, full of bornite and covellite, the blue minerals, is from Monax's Punt Hill property, also in South Australia. but in spite of intersections like this, which assay almost 50% copper, the deposit is too irregular to allow mining at a depth of several hundred meters. Exploration for IOCGs can use a number of techniques. Starting with the geophysical methods, magnetics is a very valuable tool, as IOCG systems almost always have a magnetic signature, and caused by the abundant magnetite. On this magnetic image you can see Olympic Dam deposit standing out in reds and magentas. In fact, with careful data collection and sophisticated computer modeling, you can get an idea of the distribution of magnetite in 3 dimensions, purely from the magnetic survey. The concentration of sulfides means that IOCG deposits are usually denser than the host rocks, and a gravity survey of Monax's property showed a district-wide gravity anomaly, and the mineralization, that's the oval greens and yellows, and the mineralization was associated with small second-order anomalies, which have been marked with red arrows, superimposed on the district anomaly. The gravity data of Olympic Dam shows a clear bullseye coincident with the deposit. The presence of massive sulfides also means that electromagnetic or EM surveys can be used to detect buried deposits. If a deposit occurs at surface and it's uranium rich, as in the case of Olympic Dam, except that one is buried, then airborne or ground radiometrics will detect the radiation given off by the uranium and any associated potassic alteration. Finally, if the deposit outcrops at surface, soil and rock geochemistry should detect and define the demineralization in 2D. Drilling will confirm this in the 3rd dimension. So that is a quick summary of porphyries, skarns and IOCG deposits. So what are the key points we need to remember about porphyry, skarns and IOCG deposits? Well, firstly, porphyries and IOCGs are generally very large but low grade. Skarns do not necessarily have the same characteristics. Porphyries and IOCGs are generally fairly homogeneous in grade. There may be some zoning and variation in metal ratios, but over tens of meters, grade tends to be pretty consistent. Skarns again do not fit this pattern, and they can vary considerably in grade, just over a few meters. Once you've seen a few porphyries, you've seen them all. The reverse is true of IOCGs, so that that deposits at each end of the spectrum of IOCGs can be totally unrecognizable as belonging to the same group of deposits. Porphyries, skarns and IOCG deposits very often have both oxidized and unoxidized portions. This is important as it impacts on capital costs. Capital costs for building up porphyry and IOCG mines are generally high compared to other deposit types. This is due to the combination of multiple ore streams and the huge size and throughput needed. Finally, geophysics plays a crucial role in exploration for each of these deposits. So that's the end of this talk on porphyries and IOCG deposits. The next talk in the Ore Deposits 101 series will focus mainly on mesothermal veins. This group includes one of my favorite ore deposit types, greenstone belt gold deposits, which provide a significant portion of the world's gold resources.